The next group we're going to talk about are the alkynes. The alkynes have a carbon-carbon triple bond. So our definition of alkyne here is that these are hydrocarbons with one or more carbon-carbon triple bond. Now, each carbon of the carbon-carbon triple bond has a linear geometry, and that means that the angles, the bond angles, will be about 180 degrees. The simplest alkyne is ethylene. A common name is acetylene. This is the compound that you use in an acetylene torch, so in a welding torch. All right, so the way that we draw an alkyne structure for a skeletal line structure is that we have a triple bond that has three parallel lines, no zigzags, because it's going to be linear. The condensed structure can show the triple bond or imply it. So here, what we're looking at on the right-hand side of the screen, you've got a compound with 8 carbons. Carbons 4 and 5 have the triple bond. So that's how you would draw it. So you would draw this normal zigzags, but then for carbons 4 and 5, they have to be in a straight line. So that's why 3, 4, 5, and 6 are straight, and then 7, 8, 1, 2 are going to have zigzags to them. When you write the Lewis structure, you just write the triple bond because you're writing all the atoms, all the bonds. But then with the condensed structure, you can either write the triple bond in, and that's actually the preferred method, or leave the triple bond out. Okay, so the name of this compound that we're looking at is actually called 4-octynes. So just like we did for the alkanes, the alkenes, let's break down this name. Okay, so the YNE part, that tells you, that's the ending, and that tells you specifically you have a carbon-carbon triple bond. OCT tells you the number of carbons. Okay, so in this case, we've got 8 carbons. Okay, the locator, the 4, tells us that the triple bond starts on carbon 4. Okay, so yeah, that's what the naming of an alkyne is very similar to an alkene. It's just you replace the ENE ending of an alkene with YNE. Okay, now alkynes, even though we have the triple bond, they're actually not very common in nature. One example of an alkyne compound in nature is actually this compound right here, Historenon ecoxen. Wow, I cannot say it. But this is actually, the frog on the top is called the poisonous dart frog. And so when this frog is trying to eat prey or trying to capture bugs, they have in their saliva, they're actually emitting a toxin, and this is the compound. Okay. So naming alkynes are fairly similar. You follow the same rules for naming for alkenes using the YNE ending. Okay. Only very large cycloalkynes are possible, so it's going to be very rare that you do see a cycloalkyne ring, but it is possible. There's going to be no geometric isomers as possible because it's all linear, so you don't have to worry about cis and trans isomers. Okay, so I'll tell you what, let's try naming some structures. So here we've got 3 different structures. Let's try to name it. All right, so first off, for structure A, you've got, it looks like the triple bond is on the outside. So what I'm going to do is number this to count the longest carbons, number of carbons in the longest carbon chain. So if I number this from left to right, this gives us 6, 5, 6, and we're good. So the longest carbon chain, if we name this as an alkane, should be hexane. Okay, but we know that we don't have a hexane. We got a triple bond, so this should be hexyne. Okay, so the YNE ending tells us we have a triple bond. Now, we got to number this in such a way that we get the triple bond to have the lowest number possible. The way that we already numbered it was that triple bond was on carbon 1, so that's perfect. So we just have to give the locator of that triple bond, so this would be 1-hexyne. Okay, cool. Let's try the next one. All right, so it looks like, looking at this skeletal structure, it looks like the triple bond is at the end of a molecule. We got to number this in such a way that this gets the lowest number possible. So what I'm going to do is number this from right to left. We got to count the number of carbons in the longest carbon chain. So this would be 1, 2, 3, 4, 5. Okay, so if I name this as an alkane, this would be pentane. All right, 5 carbons, pentane. I'm going to drop the A and E ending because we're dealing with an alkyne. So this would be pentyne. So the Y and E ending tells us that we have a triple bond. The triple bond is between carbons 1 and 2. Since carbon 1 is the first carbon that has the triple bond, we use 1. So this compound's name would be 1-pentyne. All right, this last one. This is actually kind of nice because it's actually done the numbering for you, so we don't have to worry about this. All right, so it looks like there are 7 carbons in the longest carbon chain. If we name this as an alkane first, if we name this as an alkane first, this would be heptane for 7 carbons. We're going to cross out the A and E ending and replace it with Y and E, so this would be heptyne. Okay. Now, with the numbering given to us, that the carbon triple bond is between carbons 3 and 4, the location, we have to give the location of the first carbon, which would be carbon 3. So this would be 3-heptyne. Okay, now this one is actually one of the first ones this is actually the first time that we've come across an internal alkyne in a problem like this. So let me show you this. So this was already numbered for you, 1 through 7. It is also possible you could number it going from right to left, okay? And if you number it from right to left, the triple bond would be between carbons 4 and 5. So again, we want to number this chain in such a way that the triple bond gets the lowest number possible. So numbering it from left to right gives us the triple bond between carbons 3 and 4. So that's why 3-heptyne is preferred over 4-heptyne. Okay. All right, so that's the alkynes. The final functional group we're going to take a look at in Chapter 10 concerns the aromatics. These compounds were originally named for their very, very strong aromas. Okay. Now that we've done structural analysis since the 1800s, there actually is a common structural characteristic to these compounds with these really strong smells. Now we know that they can all contain something called an aromatic ring. And this aromatic ring is actually shown over here. I'm going to circle this on their slide. That, if you notice that ring, by the way, this is the compound vanillin. This is the compound, the major compound that's found in vanilla beans and vanilla extract. So when you're buying pure vanilla extract, you really just want pure vanillin. That's what you're going after. Anyhow, if you notice in this compound, you have a 6-membered ring. So this looks like a cyclohexane ring, except that you have alternating single and double bonds. Okay. So, like I said, this is the compound vanillin. The simplest aromatic compound is called benzene. So benzene has a structure like this. Let me draw this in. Okay, so I'm going to draw the Lewis. Oops, I drew too many carbons. Woo! All right, so each of these carbons contains 1 hydrogen. Okay. And then there's going to be alternating single and double bonds between each of the carbons. So this appears to have alternating carbon-carbon single bonds and carbon-carbon double bonds. Now, it turns out, looking at the structure, even though you have alternating single and double bonds in this Lewis structure, it turns out that all carbon-carbon bonds are identical. So actually, it's an average of the two. So instead of being one bond or being two bonds, it actually ends up being about 1.5 bonds. So it's like 1.5 bonds. So it's not quite a double bond, but also not quite a single bond either. And it turns out that all 6 electrons are shared by all 6 carbon atoms. Okay, so this is like the first time that that scientists started looking at this and realizing that you can have more than one atom share electrons. And so electrons that are shared by more than 2 atoms are called delocalized electrons. And that means that electrons can actually move around in a molecule. So instead of being localized in one area, electrons can actually go in other areas if needed. If you remember back in chapter 4 when we talked about Lewis structures, one of the things that we talked about then was something called resonance, that you could have 2 or more possible structures for a molecule. And for a Lewis structure, and that's pretty much what we're seeing here. The reason that there are these Lewis structures is that we can have delocalized electrons. Now, these delocalized electrons, having the bonds be 1.5 bonds, okay, having all carbon-carbon bonds be identical, and then also having the delocalized electrons so they're going all over the ring, this makes the aromatic ring very stable and fairly unreactive. And it turns out that under normal circumstances, benzene will not react how like a normal alkene or an alkyne would. So that's kind of one of the cool but yet also frustrating parts of an aromatic compound. It will not react like a normal alkene would. Okay, so the way the delocalized electrons look like, it's almost like these electrons are going around in a circle. Okay, so usually when we draw a structure for benzene, a lot of times what we do to shorthand this, to show that there are delocalized electrons in this ring, we draw the cyclohexane ring, but instead of drawing in the double bonds, which we could, so remember you could have double bonds here. You could also have another structure where the double bonds are in the opposite location, like so. Because those electrons are going to be delocalized and can move around the ring, usually we kind of do a mixture of the two. So what we end up doing is drawing a cyclohexane ring, but then putting a circle in the middle. And that circle indicates that the electrons are delocalized. Okay, so that circle really means electrons are delocalized. Okay. Now, when we're looking at this aromatic ring, if you notice, here's a top view, here's a side view. There's no atoms going above or below the plane of the molecule. So each carbon atom is trigonal planar, okay? Each carbon atom is trigonal planar, and the entire ring is planar, meaning it's completely flat. Okay. So pretty cool stuff. So if we were to compare benzene with cyclohexane, both of them have 6-membered rings. Both have 6 carbons. You do have twice the number of hydrogens in cyclohexane than you do in benzene. So remember, because you have 3 double bonds, three alternating double bonds, you're going to have to take away 6 hydrogens to make that work. So that's why you only have 6 hydrogens. Okay. They're very similar looking rings, but they have very, very different chemical properties. Okay. Now, where we see aromatics come up, we actually see this in drugs. So here's actually the structures of 3 different compounds: acetaminophen, ibuprofen, and aspirin. Now, all 3 drugs have similar functions. When we have a headache, you're going to reach for one of these. Okay. Some people, and I'll be honest, some people like me, I usually go for aspirin. Okay. That's the one I prefer. Okay. My wife tends to go for ibuprofen. And, there's certain people, use different drugs because their bodies are, a little bit different. And that's totally okay. So let me explain why. So aspirin was actually the first kind of compound that came out. And aspirin was actually discovered way back in the 1750s. So when settlers were coming to the original 13 colonies, before the American Revolution, people found out that if you have a bad headache or you've got a pain in your body, and all you have to do is get a little bit of willow bark and chew on the willow bark, and somehow something in that willow bark releases some, it releases a compound, and it actually takes the pain away. So it turns out that the compound that was being reacted was something called salicylic acid, where it was almost like a precursor to aspirin. Now, there is a problem with salicylic acid. It is natural, completely natural. Like I said, it's one of the ingredients or one of the compounds that make up willow bark. So you could just literally go to the bark of a willow tree and start chewing on it, and you'll be able to get that compound. Now, if you take too much of a good, there's that saying that too much of a good thing is a bad, or too much of one thing is bad. And that's kind of what happens, because sometimes when you take too much willow bark or too much salicylic acid, it can lead to ulcers within your nose, within your mouth, within your esophagus, wherever the willow bark touched. So this was actually one of the first synthetic chemist problems in the 19th century. How do we make a compound that does what aspirin does, okay, takes pain away, but at the same time, how do we make it so that way it's not as acidic and doesn't cause ulcers? And so that's when the Bayer Corporation in the late 1890s actually came up with this compound. The actual compound name is acetyl salicylic acid. We know it as aspirin. And what we did was actually make this compound a little bit basic by adding this group right here. This CH3 connected to a carbon-oxygen double bond connected to an oxygen. By adding this group, which we call an acetyl group, we actually made the pH of the molecule closer to 6, so it's not as acidic. Okay, it's still slightly acidic, but still not as bad. But it does do the thing. It does the thing that you need it to do. Now, if you notice in these other compounds, depending on how your body is and how it can handle the compound, the pH on acetaminophen is actually closer to 7. Ibuprofen is going to be slightly more basic, so some people actually prefer to use ibuprofen. Some people prefer to use aspirin, and some people you prefer to use acetaminophen. So it really comes down to what your body needs or what your body can use. But yeah, if you notice, all 3 of these compounds have similar features. There's going to be 2 chains that come off of the aromatic ring. Okay. It could be 2 chains. Now, if you notice, the other thing is that some of these structures actually have a carbon-oxygen double bond. So, like, for instance, this one's got one here. This one's got one here as well. Okay. So there's actually parts of molecules that actually do something for the human body. And that's what we call a pharmacophore. So this is actually not in your book. So let me explain this part. So a pharmacophore, what that means, this is the part of the molecule or drug that gives some sort of physiological response. So yeah, that's what we call a pharmacophore. So by looking at each of these structures, there's things that are common between these structures, and sometimes there's like patterns in these molecules. So if you notice how you can take a certain drug, and then within a couple years there may be like a knockoff drug, okay, or an off-brand drug. All they're doing, these companies are copying the drug of that they know does some sort of physiological response, and they're modifying the drug just slightly, so that way they're making the compound different, but they're keeping the functionality of the drug intact. Pretty cool stuff. All right, anyhow, back to this. So we need to draw a Lewis structure for benzene. So the Lewis structure for benzene, you're going to have a ring with 6 carbons. So let me draw all 6 carbons here. Now remember, Lewis structure, we got to show all atoms and all bonds. Okay, so I need to show alternating single and double bonds. So let me draw in 3 double bonds. Each carbon is going to have 1 hydrogen. Okay, and there it is. That's your structure for benzene. Okay, so the last thing we're going to do in this chapter is talk about how we name compounds. And we've been talking about this for a while. So we've been talking about straight chain alkanes, alkenes, alkynes. And I started on Tuesday to slip in some compounds that were substituted. What if you have a substituent coming off of a chain? How do we deal with that? Okay. So a lot of the stuff that I'm going to say here is not necessarily new. It was stuff I was saying last session, but now we're formally saying it. So here we go. In the IUPAC system, a branched chain hydrocarbon is viewed as a straight chain or a ring parent with a chain of carbon groups substituting for 1 or more hydrogen atoms. Okay. The chains of carbon groups that replace the hydrogen atoms on the main chain are referred to as substituents. Okay. IUPAC names often involve identifying the parent chain and then identifying the type and location of the substituents. So the way that we deal with this is that we identify the longest parent chain. So we identify the parent chain. That's the longest continuous carbon chain. Okay. So this is step 1. Identify the parent chain. You want to find the longest continuous carbon chain. Second step is to assign the parent chain a name. Okay. Once we do that, if there are 2 chains of equal length, okay, select the one with more substituents to be the parent chain. All right, so if you got 2 chains, if you number this and you got 2 chains, they're equal length, you're going to go with the one with the more substituents. Okay. Now, substituents that are alkane-like, meaning they're only carbon-carbon single bonds and carbon-hydrogen single bonds. These are called alkyl substituents or groups. And alkyl substituents are named based on the number of carbon atoms plus a YL ending. Okay, so an example of something like this is here is a Lewis structure. Okay, so the longest carbon chain has 9 carbons, and on carbon 3, we have a CH3 group coming off of that. Because you have 1 carbon, we call that methyl. Okay, for carbon 6, you got 2 carbons coming off of that group. 2 carbons would be ethyl. Okay, and then what we're looking on the right-hand side, that's your skeletal line version of what we were seeing. Okay, so let's review what we got so far. So the first step, identify the parent chain. Second step, assign the parent chain a name. Okay, so we identify the parent chain, then assign the parent chain a name. Third step is that we number the parent chain starting at the end closer to a substituent. Okay. Fourth, assign locator numbers to each substituent using the number of the carbon of the parent chain to which it's attached. Using the number of the carbon of the parent chain to which it's attached. The locator number is placed before the substituent name followed by a hyphen. Okay. All right, so again, step one, identify the parent chain. That's your longest continuous carbon chain. Step 2, assign the parent chain a name. Step 3, number the parent chain starting at the end closer to the substituent. Step 4, assign locator names to each substituent using the number of the carbon of the parent chain to which it's attached. The locator name number is placed before the substituent name followed by a hyphen. Step 5, if there's 2 substituents on the same carbon atom, the locator name is listed for both substituents. Okay. All right. Okay. Now, so looking at this, let me give you an example. Let's say I want to draw this compound. Okay, so in this compound, you've got, let me draw this. Okay, so here's your compound. Let's follow what we're doing. So we got to count the number of carbons in the longest carbon chain. So I'm going to number this. Let me do this in a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 carbons. That would give us, if we name this as an alkane, this would be nonane. Okay. Now let's identify our substituents. So on carbon 3, you've got 1 carbon, so that would be a methyl. So what I tend to do is just make a list of all my substituents and where they located. All right, so in carbon 6, you've got 2 carbons coming off of that. That would be ethyl. All right. So putting this name together, nonane is going to go on the end. But you've got two substituents. You've got methyl and ethyl. Which one comes first in the alphabet? And that's going to be ethyl. So this name would be 6-ethyl. Okay. Now we got to write the methyl part. So I'm going to use another hyphen and to connect the other part, 3-methyl. Okay. Now that all my substituents are named, then I can add the nonane. And there you go. That would be the name of this molecule. Okay. So there's a couple more rules. Let's knock those out. So the last three rules that we talked about was that we number the parent chain closer to the end of a substituent. We assign locator numbers to each substituent. If there are two substituents on the same carbon atom, you list them for both substituents. So when we're assigning a locator number, when the same type of substituent appears on more than once, we use a multiplier prefix. Like di, tri, tetra, etc. Okay. In these cases, list all of the locator numbers. Before the prefix. Okay. So this is going to be the sixth step. When you're assigning, when you've got the same type of substituent and it appears more than once, you're going to use di, tri, tetra, and so on. All right, we're on the home stretch. Okay. Finally, when you're putting the names together, you write the substituent names with the locator numbers in alphabetical order. Followed by the parent name. Okay. Now, sometimes let's talk about some things that may happen too, just in case. So let's say you're dealing with a ring structure and your longest chain is a ring. Cyclo is going to be your prefix for the parent name. And we talked about ring structures before. That the name, you're going to name it like an alkane, but then you tack on cyclo to indicate that you got a ring structure. And in the name, the prop, bute, pent, that part of the name is going to indicate the number of carbons. All right, now, how do you deal with a ring structure if you've got substituents? So the way we do this, if there is one substituent, no number is necessary because we assume that that's going to be carbon 1. But if you have two or more substituents, we number starting with the substituent that gives lower numbers to all substituents. So you want to number this so when it comes to ring structures and you've got two or more substituents coming off of a ring, you want to number the ring in such a way that all the substituents in the ring gets the lowest numbers possible. Okay. Well, let's try this out. So let's try to name a couple compounds. So here's compound A. Let's follow our rules. So we got to number this in such a way that we figure out the longest carbon chain. So I'm going to start from left to right. 3, 4, 5, 6, 7. So with 7 carbons, the parent name should be heptane. Okay. Now we got to identify a substituent. It looks like on carbon 4, you've got that substituent. Now we've got to number this carbon chain so that way that group gets the lowest number possible. But for this molecule, it doesn't matter if we number its left from the left or from the right, it's still going to be carbon 4. All right, so it looks like this substituent has 1 carbon on carbon 4, so 1 carbon is known as methyl. All right, and then since that's our only substituent, if we put this together, this name would be 4-methyl, and then we add the parent name heptane. And there you go. That would be the name of this compound. All right, so let's try the other one now. All right, so we're going to count the longest carbon chain, and we got a Lewis structure, so we're going to have to work a little bit carefully. So it looks like if I start here at the bottom, 1, 2, 3, 4, 5. 5 carbons. Okay, so 5 carbons would be the pentane. And it looks like I'm going to have a substituent here and another substituent over here as well. So I've got to number this chain in such a way that those substituents get the lowest number possible. So if I number this from left to right, the substituents would be on carbons 2 and 3. If I number this from down to the top, this would be on 3 and 4. So we want to number this with the substituents on 2 and 3, and it looks like you've got a methyl group on carbon 2, and then it looks like a methyl on carbon 3. So to combine these two together, this would be 2, 3 dash dimethyl. Okay, so that's your substituents. And then after that, we just tack on the parent name, pentane. And there you go. That would be the name of this molecule. Cool. All right, so what if, okay, so that's dealing with substituted alkanes and cycloalkanes. What if you have a substituted alkene or an alkyne? So it actually works pretty much the same way as the other times. So we locate the longest continuous chain that contains both atoms of the carbon-carbon double bond or carbon-carbon triple bond. Okay, we assign the name using ENE or YNE, depending on what we got. At the end, we number the parent chain from the end closer to the double or triple bond, and provide the locator. Okay, we identify and assign locator numbers to any substituents, place them in alphabetical order and in front of the parent name, and then if we're dealing with an alkene, if we're dealing with an internal alkene, then we use cis and trans prefix, if appropriate, in front of the name. Okay, so let me give you an example. What if you have this compound, 2-ethyl-1-butene? Okay, so let's start with the parent name. Butene says, ENE says you've got a carbon-carbon double bond. You've got 4 carbons, and that's the but part. And then carbon 1 is going to be the double bond. So let's just draw what we've got. We've got 1, 2, 3, 4 carbons, and we know the double bond is going to be between carbons 1 and 2. And then you've got a substituent on carbon 2, you're going to have an ethyl group. So on carbon 2, 1, 2 carbons. All right, and that would be the answer to this question. That would be the structure of 2-ethyl-1-butene. Okay. All right, what if, let's try another one. All right, so here we want to name these compounds. Okay, so thing we're going to do is number this in such a way that we get the lowest number possible. We want the biggest number for each carbon chain. So 1, 2, 3, 4, 5, 6, 7. All right. So it looks like you're going to have substituents coming off of carbon 3, and then you're going to have a substituent coming off of carbon 5. All right, so 7 carbons should be heptane. But we need to name this as an alkene, so we replace the ending with heptene. And it looks like that double bond is occurring between carbons 3 and 4, so that should be 3-heptene. Okay. Because you have you've got a carbon here, carbon 3 actually has no hydrogens here, we can't use cis or trans. Okay, so usually you want to have something where you only have one hydrogen on each carbon of the double bond. That you don't have, so you don't have to worry about cis or trans with this one. Okay. All right, so it looks like on carbon 3, oops, circled the wrong one. Carbon 3, you've got 2 carbons coming off of that, so that should be 3-ethyl. And then on carbon 5, it looks like you have 1 carbon, so that should be methyl. All right, so putting this name together, it should be 3-ethyl dash 5-methyl dash 3-heptene. And there you go. All right, so let's try the next one. All right, so we want to number this so that way we get the longest carbon chain. So in this case, we got 6 carbons, and the double bond is going to occur between carbons 2 and 3. So 6 carbons would be hexane, but we replace the A and E ending with E and E, so it's hexene, okay? And since the double bonds between carbons 2 and 3, there should be 2-hexene. Okay, now looking at both of these carbons, there's no hydrogens on each of these carbons, so cis and trans doesn't pertain here. So we're good. 2-hexene is good for this compound. So it looks like you got a substituent on carbons 2 and 3. So it looks like you got a methyl group on carbon 2 and another methyl group on carbon 3. So we would want to write this as 2,3 dash dimethyl. And then connect the parent name 2 dash hexene. And there you go. There you go. That's how you would name these compounds. All right, finally, the last part. What if you've got to name a substituted benzene? So in this case, you're going to deal with your parent name is going to be benzene, okay? If you have one substituent, you don't need a locator number because that's all going to assume the carbon with the substituent is going to be carbon 1, okay? Now, that being said, many substituted carbons already have common names. So we know if we have a methyl group coming off of benzene, we would say that we would name that as methylbenzene. The common name of that is toluene. Okay. You could also have a propyl group. You could have an ethyl group. Okay. So the way that we do this is that to name a substitute benzene, we assign locator numbers to give the relative position on the rings. Possible locations for 2 substituents would be on carbons 1 and 2, carbons 1 and 3, or carbons 1 and 4. And what we do is list those groups alphabetically. Okay. All right, so let me give you an example of how this works. All right, so here you've got a benzene ring, and it looks like on one carbon, you've got a methyl group. Okay. And then the other one, you've got 1, 2, 3, 4. That would be 4 carbons, so that would be a butyl group. Okay. So it looks like it's going to be 1, 2, 3, but which group actually gets the number 1 position? So the way that I usually deal with this, and this is going to work for what you got to do. The bigger group gets the first number. So in this case, you got 4 carbons for butyl. You got 1 carbon for methyl. Butyl would be the carbon 1 position. methyl would be 3. So this would be 1-butyl dash 1-methyl benzene. Okay. For the next one, you got a benzene ring, and you've got groups of carbons 1 and 3 position. You got a methyl group, and you got an ethyl group. So since ethyl is bigger than methyl, make ethyl the carbon 1 position. That would make methyl the carbon 3. So this would be 1-ethyl dash 3-methyl benzene. There you go. All right, and that, my friends, covers all of the nomenclature that you are responsible for Chapter 10.